So here's David. I know that number. Tell us your number.
1,729.
Does anyone know why David picked 1,729?
Isn't that a power of 3?
729, yes. Is a power of 729.
It's the lowest number that's the sum of two.
Yes, let's see. So what is special about 1729? And that is that, I'm sorry, say that again.
It's the lowest number that's the sum of 2 cubes to different ones.
And what are those 2 cubes?
It's 12 cubed in 1 and 10 cubed in 9.
Oh, that's exactly right. This is a sort of a remarkable number from a number point of view. You can do something to get this number that you can't do to get any smaller number. You can add 2 cubes or these 2 cubes and you do the same thing anyway. And there's even a story behind that. Does anyone know the story? It has to do with a famous Indian mathematician named... Oh, and if we know the first name and the last name. Good. So you know the story?
Yeah.
Okay, let's hear the story.
He
His story.
was dying in the hospital, and his friend came and visited him, and he said, my taxi number was 1729. It's an unremarkable number. And she was the examination said, oh no, it's not. It's the lowest number. It's the sum of 2 cubes.
Like, right. He just like, he says, oh, that's special, because I know 17. I don't know how, yeah. This was a man who lived kind of in the world of numbers practically nonstop. And so that sort of thing was clear to him. He's a remarkable fellow. What other objects do we have here? We'll wait a minute or two before we get sort of officially start. Adam, what do you have there?
Collapse conjecture.
Oh, how does that go? Can you?
Yeah, x goes to x over 2 if x is even, or 3x plus 1 if x is odd.
Oh, so this is so x goes to x over 2 for x even, and 3x plus 1 if x is odd. This is sometimes called, sort of the more familiar name is
3n plus 1.
Yeah, there's this 3x or 3n plus 1 conjecture. And what is so remarkable about this, or of interest?
If you repeat it, it always goes to 1, but it's not proven.
So you start with some number, like pick a number. All right, let's get a number from here. I haven't met you yet. What is your name?
My name is Kate.
There we go.
It's just Catherine.
That's,
It's with spell.
I'm with you. So Kate, that's lousy. So pick a number from, let's say, 1 to 20.
7.
7. What's the number I was thinking, actually. So we're going to play this game with 7 and see what happens. This is a great chance for you. So let's go to Lucinda. Okay, Lucinda, is 7 even or odd? Give her a So we do this, and that leads us to what guy? We take 7. We're going to walk through. This is a weird. Have you ever seen this sort of notation before? No, I didn't think so. I haven't seen it yet. So what we have to do, apparently, if the number we have is odd, we triple it and add 1. But if the number we have is even, we cut it in half. Like, that's how to read this. That's what it really means. So your number was odd, so if you have 7, what does it turn into? That's the tripling part, yep. And then the final result is 22, which means we have to come here.
Oh, that's me.
Because 22 is your number.
Well,
this is Cassidy.
Yeah.
Now, what happens to 22?
What do you mean?
I mean, which rule do we use?
Oh, the even one.
We use the even one.
Yeah.
And what happens to 22 when we apply this little rule to it?
We don't know.
And out comes?
What is that? I forgot.
That's
11.
your job.
Oh, yeah. 11.
11. Now, we haven't gotten to 1 yet, but Adam says that if we keep doing this over and over, we keep following this rule, we're guaranteed to get to 1. You believe it? Well, let's find it. Okay, so let's keep going. So you get to do it next. 11 goes to?
34.
34. 34 goes to?
17.
Yep. That's a tough one.
Yeah.
Oh, if you play Pinochle.
You can call a friend.
Andrew.
I'm not telling you that.
I guess 53.
So we have a
54. Yeah, the 1.
Something in the 50s, 53, 54, are you with it?
I think 52.
52, well, what is 3 times 17 anyway?
50.
What does it end with? What's the last digit?
One.
It's a 1. Yeah, so 52 is a good bet. And then where does 52 go? We're over to Dalton. 52 divides to 27 if you cut it in half.
No, it doesn't.
So you just, oh, I'll bet you cut it in half and added 1. So we just cut it in half. So now we're at 26. We have 1 yet? Just check. All right, I don't know how we feel about this, but I don't see 1 on the horizon. All right, so where does 26 go? Oh, so what we're doing is, if it's an even number, we cut it in half. If it's an odd number, we triple it and add 1. So 26 falls into which category? Even or odd? Even. And so we cut it in half, and that gives us 13. Nothing to it. It's actually, after a couple of tries, you'll become convinced that this is actually pretty simple rules, like the cutting in half or something. So we're at 13. But now guess what? We were trying to get to 1. But 13 blows up again because we have to do this. We get to, well, if we have, let's see, 13, you have to triple it. 39 and add 1. Now we're at 40. Oh, we like 40 though, right? Because now what happens at 40, Sailor? And then 20, we're on a roll. 10.
What? Oh, 5.
5. Oh!
15. Wait. Oh, 16.
16. And now you can write, the writing's on the wall. 16 just cuts in half, 84, 2, 1. And sure enough, we get to 1. Like, so give yourself a second. We got to 1.
Should we officially start?
Yes, yes. We're still just playing around. That, we can all thank Adam for writing that on his post-it note.
Brilliant. Well, let me say welcome. This is a special session of this math conference, Sigma for Math Circles. And thanks so much for coming. This is great. You've obviously met Dr. V. I know he's calling himself Dr. V, I've noticed. So this will be a fun session. For those at the back, the simple rule is feel free to just be here, but remain silent. This is the kids' experience. So off we go. Have a grand time.
So now that I have convinced you to at least put your names up front, we're going to, I'm going to tell you sort of a story. It will be a mystery, and we need some participation on the part of the audience in order to act out this story. So you don't know what you're getting into yet. So I want you to volunteer anyway. I need 7 volunteers. Here we go. I'll take any 7. Katie, was that a pick me?
Yes. I wasn't picking with who.
Katie. Katie is 1, and
Nina.
Nina is 2, and oh, that means I get to pick the other 4, right? Who has to? Well, okay, well we have to rope Sailor in. So Sailor's 3. Who else? Sailor, you get to pick someone now. Hey, Eric is 4. Let's see. We had Nina and Katie and Sailor and what's Eric? Harrison. Harrison's 4, and then we'll get 2 more. Here we are. 2 more volunteers from over here. So you are. Here you go. I'm going to just hand these out. 1, 2. Hang on to your post-it. 3, 4, 5, 6 for Nina. So here's how the story goes. You are the players in this story. Actually, maybe we'll have Emily. Here's the story. Emily, being the good student that she is, has this lovely flash drive on which her entire book report. What is it that you're assigned these days? Like, what's a really big project that you have to do? A book report. Right? And she spent the last 2 weeks working on it, because you started early, because you're a good student. And it's all ready for turning in and turning out or whatever, and it's on this flash drive. And she's in the library just checking one last thing, wanders around the library, sets it down to reach a book off a shelf, and leaves it sitting on the shelf and walks out of the library. Because a friend came by and you got talking, right? You got this. So off you go. And about 30 minutes later, Emily realizes that the flash drive is gone. Bye-bye flash. Actually, I don't want to lose this song. My talk is on here. Now, as soon as she realizes, of course, she runs back to the library. Guess what? It's not. The flash drive is gone, and Emily is distraught. Fortunately for Emily, there's a hall monitor that has been outside the library the entire time. That's me. And the hall monitor happens to know that the following 6 individuals all entered the library. Now, I get a little confused on the order of things, so I can't actually remember when they were in there, but I know for a fact that the following 6 suspects, that's suspect A, we're going to not call them by name to protect the innocent. There's suspect A and suspect B, and C and D and E and F. And so it's time to talk to these 6 suspects. Come on up, suspects. Let's form a little circle here. Now, I want to know, I'm going to interview each of you. I want to know, and let's put you in order so you can sort of, in fact, let's put you in order this way. So let's put A through F kind of around here. It's a little tight, but we're all friends. Now, so we're going to go down the line. I want to know, suspect A, did you see anyone else in the library while you were kind of wandering through the stacks?
I saw B and E.
Okay, and just point at them for me, will you? There's B, you saw B and E. Okay, well, that's very interesting. Now, suspect B, I want to know, did you see anyone in the library while you were present?
Yes, I saw A and F.
Now, I like that because, see, B saw A and A saw B. So their stories are collaborating, they're corroborating one another. Tell us, suspect C, who did you see in the library?
I saw D and F.
Okay, that's nice. Likely story. Suspect D, who did you see in the
I
library?
saw A and F.
Now this is very interesting. Tell us again, who did you see?
B and E.
There's A, but you saw
A and F.
A. Now I want to know, is this a problem? So you saw A in the library, but A doesn't say he saw you. Is that an issue? Because A saw B and B saw A, and that all kind of lined up. I want to know, does that mean that this is the guilty party?
Yes. That's fine.
Thanks for your input, suspect C. But I'm asking our impartial jury here. Is it a problem that suspect D saw suspect A, but suspect A did not see suspect D?
Maybe suspect he was hiding.
Maybe he was, like he was behind the shelf somewhere. And in other words, is there anything contradictory in one person seeing another, but that second person not noticing the first person?
Maybe he was blind.
It's like one of those 20 questions stories, right? And he was a midget, and he was a balloon, right? How do you feel about that? In fact, there's a lot of that going on, because who did you see?
Oh yeah, A saw B, but I didn't see A.
Okay.
I saw B and C.
You saw B and C. And then, yeah.
C and E.
I'm sorry, suspect F. You saw C and E. So this is a real tangle. And here's the deal. I suspect, as hall monitor, I have these intuitions about students, that most of the students are telling the truth. But I propose to you that one of you has invented a person that you are claiming was in the library who wasn't actually there because you're trying to frame them. But it's a little tricky to tell, just based on this information, who the culprit is. So do you have the story so far? So suspects, you can all return to your seats. We needed the dramatic enactment just to help fix this story in your mind. Because now it's time to solve this mystery. And that's largely going to be up to you, because like I said, I, as a hall monitor, am easily confused. But I'll help kind of get things going. For instance, I'm going to propose to us that we need a good way of of somehow organizing all these clues. And I wonder if anyone can, and I have something in mind, and I'll help us figure it out. But I wonder if you can think of a way to organize all of this information that will help us sort of deal with it. A table is a very natural way of setting it up. So let's see, what would a table look like?
Suspect, who they find.
So we've got, so I want to put it this way, like suspect, we get A, B, C, D, E, F, and then who they saw. Let's run through that real quick.
I saw B and E.
Okay.
C and E.
Wait a minute. You saw yourself? Oh, I see. We're on P.
This is,
B and C. That was kind of E saw B and C, and then F saw
C and E.
C and E. Okay. So is it becoming clear? I would like a more visual, pictorial way to lay this out.
You'd have like A, B, C, D, you'd have like arrows for each
All
side.
right, so here are all our people, right? A, and B, and C, and D, and E, and F, something like that. And then we have who saw whom, like here, I'll get another color. So A saw B and E, like that, and then B saw A. I'll just go back, and F, and C sees D, and F, and D sees A and F, and then E sees B, C, and F sees C, back to C, and E. So that's, maybe I could have drawn that a little more neatly. So now I have two ways of looking at it. Got it yet? What's that? Multiple people. Oh, our line. No. Oh, remember, it's okay if one person sees the second, but the second doesn't see the first. Like maybe one person was just walking out one aisle and the other person was coming in, and so I saw them, you saw them down the row of books, but they had their back to you or something like that. This is where, so when mathematicians, it's time for the moral of the story, I'll just tell you right now. When mathematicians have to deal with something as messy as this, they have a standard go-to strategy. Can you guess what it is? So here I have a messy question. How do I tell which of these little arrows can't be possible, can't be consistent with all the others? And it's too much of a mess for me to figure it out at first. So what do mathematicians do when they're faced with a messy, difficult problem?
Make assumptions.
Like, say, well, you say like, well, let's suppose that this is the one that was lying, and sort of take it out and see if the rest will work. That's a good idea, and we'll put that into play in a little bit. What else did they do? Any idea? I want to tell you. I want you to remember this. And here's the strategy. Go-to strategy. You have a hard problem that you can't solve. Then you make up an easier problem that still retains the essence of what you're trying to figure out, but an easier problem that you can solve. So that's our go-to strategy. So we're not going to deal with this for a little while. In fact, if this is two-sided, which it is, Dalton, do you think you can give me a hand turning this around? We're going to...
Maybe it just flips that way.
Does it just turn over? Is there a flip on one? It might if we knew how to unlock it. Or we could just turn it around. All right, we're going to go with the original strategy. There, is that better? This one. Okay, so here, let's play around with this a little bit. So let's make some much simpler little graphs and see if they could represent. Oh, by the way, this little set of points and arrows I'm calling a graph. Have you ever heard it called that sort of thing? It's usually a graph, right? Is you use your calculator, you get the little thing, and the little curve. So these are also called graphs, but it's a completely different meaning of the word. So I need someone here. I'm going to draw 3 dots, and I'm going to give the marker here to Alyssa. I'll give the marker to Alyssa. Can you draw some edges between those 4 of us?
Edges?
Edges are the little lines that connect one dot to the other. So you can pick how many edges. You can do it however you like.
Triangle?
That counts.
There you go.
There's your graph. Now, I want to know, could this be a timeline graph? So I'm going to call this a timeline because these are going to represent 3 people, these dots. And these are going to represent whether they were in the room at the same time, so one of them could see the other. So let me write all this down and then we can play with it. Could this be a timeline graph? And I'll label our little player. These are the people. And this little edge that Alyssa drew means that person B and person C were in the room at the same time. And the same for the other edge. Means B and C were in room at the same time. So the question is, can you imagine a way that 3 people could come into a room and out of a room so that they overlapped in that manner? Or is it impossible? If you don't like the graph, is there a way for 3 people, do you think, to, what do you say? So we have, go ahead, Adam.
Yeah, they get out in the room at the same time.
Right, you just, like, 3 people walk in, they all overlap, right, in the room, and then they all walk out again. So we could, here, I'll draw a timeline. Here it is, time. And maybe maybe person A entered the room and then left a little bit later. You see what I mean when I draw this sort of thing? Like, this is the time, the part of the time that person A was in the room. And then maybe person B entered the room and left a little bit later, and maybe person C entered the room and then left pretty soon. But they were all in the room at the same time at one point, and so of course they all overlapped. So this could be a timeline graph. Well, let's make another graph. Let's get Sam. Now, this time, let's try four people. So, yeah, you write however you like, find a little space. Now we got 4 people. It's kind of like a little puzzle. He's going to draw the graph, and then we're going to try to create a scenario which would correspond to it. Let's see what he does. Are you happy with it?
Yes.
Okay. So we'll call this person A, B, C, and D. Go ahead and give it a try. You can write on, it'll help to experiment a little bit. You've got Post-it notes and there's some pens floating around, or you can work on the whiteboard, or you can look over your neighbor's shoulder, you can just think about it in your head, whatever you like. Let's see if Sam's graph. Oh, good question. So, what was your name? Valerie. Valerie wants to know, can you come in more than once? And it's sort of, it depends. In the mystery, each person went into the library once and then came.
A few extra pieces.
Oh,
Much, but
a little paper. Let's go. You take one. In fact, why don't you take one for each two people? Pass it around so you can. It'll help to be able to muck around a little bit. In our mystery, each person came in and then left and never came back. So maybe for now, I'll suggest that we only look at that sort of situation. Although certainly there would be nothing to stop us from investigating what would happen if people could maybe come back twice or like, see where that all led. Absolutely. So we'll just play around. I'll let you think about it for a little while. And if at some point you feel like you either have a scenario that would correspond to the graph, let's draw it up here. Or if you think that you can convince us that it's impossible, then we'll let you try to figure that out too. So you want to... So this means that A and C were in the room at the same time, and A and B were in the room at the same time, and B and D were in the room at the same time, and C and D were in the room at the same time. So, is there a way for that to happen? And we'll paper. Let me get it around the back. That's right. A and D, and neither can B and C. That's what that picture means. Exactly. Exactly. So you gotta wait. Oh, I see. Right. That would give you a picture where every pair of B and dots had a line, right? Because they were all in the room. So what you've got is a way to do this one, where if we draw them all in.
Yeah.
Yep. How are we feeling over here?
Can C come in these? I don't know.
Oh, we decided not to allow that for now. Although it'd be interesting to see it. So have you got a way to do it if C can come and then leave and then return?
Yeah.
Okay, well let's see how that can happen, and maybe we can fix it. Like maybe we can patch it up, and so that C only comes once. Katie, would you be willing to show us how to do it if we let C come into the room twice?
Yeah, okay.
And then maybe that will get us going somewhere.
Go ahead.
Yeah, come on, go ahead. So give us a timeline that corresponds to that, to Sam's graph over there. Okay, so A comes in for a little while.
And then B from each group.
That's
It's not here. And then it comes. And then D stays one.
And B comes in after A and leaves after A as well. So they do overlap. And that's good because we want A and B to be in the room at the same time.
And C does not overlap with B.
So C comes in but leaves before C. Pardon, before B. Yeah.
And then B goes. Yeah. And then D is here, and so C. Does B, C, D? Yeah, B, C, C.
Well, let's take a look at this and so take a look at what Katie's drawn and tell us if this timeline really does correspond to that timeline graph.
No, because C and D overlap.
Oh, yes, so C, oh, right, we don't want C and B to be in the room at the same time.
It wasn't the way that I wrote it.
Got it. So does that fix it?
Yeah.
If you move, I think if you move C back a little and then extend B a little. Because then if you move the second C back, then B
What's,
and D can overlap.
what's the problem that you see there now, Valerie?
Because B and D don't overlap and they need to.
That's true, B and D need to overlap.
So
If
if
you
you make
just
C,
extend
if you just
the
extend D a little bit.
Now,
But B
B,
needs to overlap with A too.
Does CCA and CC's.
now B and C, this is, boy, we're making, you kind of see what we're trying to do though, right?
Can B come in this guy? Before, after C, for B. But then it would be.
Oh, I see, so B is here in between C.
Oh yeah, D can come in here. Yeah.
Except A and D can't overlap. So A needs to go back a little.
Okay.
Well, I'll tell you what, this looks like it would benefit from a fresh start, or unless we have it. Is it good now?
I think so. Okay. So B is A. Sorry. Or there. Now. B is okay. B overlaps with A.
So B overlaps with A, that's good. Yeah, we want
A
that.
overlaps with C.
A overlaps with C.
D overlaps with D.
Yep, and then C overlaps with D. And is it the case that A and D do not overlap?
A and D overlap.
And B and C, oh man, B and C.
Because I can't, because I can be in between.
Oh, I see. So that there are these sort of, there are these dividing lines right here. They
D
don't
rushes in.
overlap and
Yeah.
they don't overlap there, something like that.
While the C is in the bathroom, B ropes it.
Got it. Are you happy now? Does that, here, why don't I let you just move to one side so we can, does this graph, does this timeline really give us that graph? Looks good?
Yeah.
So there's a way to do it if we let C go to the bathroom. Now the question is there a way to tweak this a little bit so that each person only enters and leaves the room once?
Can I put D in the very, very beginning? Like, C comes here. D is not C. Okay. D. The DC is C.
So while Katie's playing here, we're going to take a vote. Just to kind of feel where everyone is. So I want you to take just a couple of seconds and decide for yourself whether you think it can be done with only allowing each person to enter and leave the room once, or whether it's impossible. It's one or the other.
I don't think it's possible. Although I think I can do
me take the pen. This is very good. Thank you, Katie, for. I really like the idea of, like Katie said, well, let's break the rules a little bit. We could do it if we let someone come in twice. That's a great, breaking rules is a good strategy. Find a way to do it, and then maybe from there you can find a way to do it that's even, with even greater restrictions. And that's a good idea, way to play with it. So, you ready to vote? So, how many people think it can be done? How many people think it's impossible? Would anyone like to try to convince us it's possible? Because you're correct. It's actually impossible. But what's the, where's the catch? All right, let's see what, maybe I can give you a little, is it okay, Katie, if I give us some space? I'm going to take this off, maybe this off. I think we kind of know the game by now. Okay,
So A and D can't be in there at the same time.
all right,
So it's going to look like this. Or maybe D could be first, but that doesn't make a difference.
so I want to interrupt lots, if that's okay.
That's fine.
Are you okay with the way he's drawn it so far as being perfectly general? That it doesn't really matter if D was first or second because the picture looks the same. So far good. This is perfectly general. This covers all possible cases in a sense. Okay, now.
So B is in there with both A and D. So it's got to somewhere intersect A and somewhere intersect D. So we can draw it like this. It could go off farther than A, or it could go off farther than D. But the important thing is now there's no possible way that we can have C intersect both A and D without also intersecting D, which we can't do.
Are you convinced? So you're saying that B has to cross, sort of overlap with A and D, and that forces B to stretch all the way across this middle spot. But C also overlaps with A and D, so C also has to go across that middle spot, and so that forces B and C to be in the room at the same time, which is bad.
Right.
You buy it? I think that covers. I buy it too. So let's agree that this sort of thing is impossible. By the way, can you think of a nicer way to draw this graph? Can you untangle it a little bit for us without really changing it? Yeah. What if we switch A and B? Then what would it be drawn like? So that B is up here and A is down there. Now what does the graph look like? Yeah, then it's basically a square. These are actually the same graph. We just drew it on the board a little differently. But everything's still connected up the same way. It's the exact same puzzle. Just this will come in handy when we get to the back. This idea of untangling our graph to make it a little neater to look at. Okay, great. Now, I'm going to give you two very thought-provoking graphs to consider, which will lead us to the point where we can solve the mystery. You're well on your way to kind of understanding when some picture does represent a valid timeline and when it's impossible. Right? This is what we do when we study something as mathematicians. We start to make little cases and gradually understand what works and what doesn't. So here's the graph I'm going to show you next. And I'll pick this one because I have a very special one in mind. It isn't going to show up with that marker. I'm thinking of this graph. Now I've got 7 people in the action. A, B, C, D, E, F, and G. But you're now you're getting good at this. So you've got some paper, and I think that at this point, I'll let you play with it. Can it be done? Is there a way for 7 people to overlap in a room? Is there a timeline that would lead to this picture? See what you can do with it. This is the V challenge.
Okay, so can C only see D and F? Like that's the only one that can see 2 people, right?
C is, that's right, C is in the room at the same time as D, and F, and B.
Oh.
So they all are in the room at the same time at some point.
Yeah.
C with all of the others, but B and D and F, none of them are in the room at the same time, because I didn't draw a line between them. So that's how to read the graph. Yep, you got it. Now, maybe, so you might be right away convinced that's impossible.
All right.
Or maybe that you right away see how to set things up so it happens. This is a good place to start though. You homed in on it right away. Can you see all right? Yeah.
They still connected to button.
No, let's only allow people to come in and leave once in this. I mean, it's a good question to ask. If it's impossible in one way, maybe it's possible in a different way. So we'll, at least for starters, we'll try to do it just one. Draw C for starters. C is kind of where all the action takes place. So let's give ourselves a little time. Draw C. All right, so here's C. Okay, so C is in the room kind of from this time to that time. C has to be this. C has to overlap with E and D and F, but none of those two can overlap one another. So if you do this, 3 people overlap. E and F. No, that's a good idea, right? So there, that could be terrific. Now let's see if we can just get those last couple in there. You ready? One label B is not going to deal with that. All right. We got our 3 people. And now, can you give me G? It only is in the room at the same time as F. Somewhere on that. Oh, yeah, so we can get G on there. Good. And what's next? A only overlaps with B. And then Q only overlaps with B. Yeah, there's A. Excellent. And then finally, E only overlaps with B. All right. Any ideas so far?
Well, could A, B, C, F, and G all see each other and A, B, C, D, E? Or is that?
Oh, if A, B, C, F, and G all overlapped in the room at the same time, then we would have drawn in all these little edges there. But since there's nothing from A to E, or A to F, and A to B, then they weren't in the room at the same time. So I'm just curious, any initial thoughts? Nina thinks she's pretty sure it's impossible. Not feeling good about it. This one I forgot. Drew came upon the same conclusion. So there's a lot of pessimism here. And again, you're correct. This is actually, it's a different sort of configuration than the square, but this kind of thing is also impossible. And I've asked Andrew if he'd be willing to come and kind of show us, give us a rough idea of why that's true. And then it will be time to solve the mystery. We're going to do it in 10 minutes. We've like pretty much got everything we need. All right, there's C.
This is our only problem. B can come off. A can come off.
Right, because A is only overlapping with B. And looks like it's possible to do that. But yeah, what happens in the middle?
You can't overlap E without overlapping C. Or you can't make D and E overlap without over C, unless C can stop and come back.
Right, so I guess that answers Katie's question at the same time. That if C can go to the bathroom again, C is always the one that's easy to go to the bathroom. So that's how it is, right? There's always that kid. It's the same one every day. Does that make sense to everybody? You want this, like, ideally, you want this much to make sense, because now we're about to put it to work. Here, there's no way to make E overlap with D without also overlapping with C, and so we're stuck. Okay. I'm going to tell you a sort of famous result from graph theory. It was proved in, I believe, the 1960s, which is not all that long ago in sort of mathematical time. Very recent sort of proof. It said the way to tell if a particular graph really corresponds to a timeline, so there are only two things that can go wrong. Either this sort of thing, or the graph that Adam drew earlier, which was the square. And this is the theorem, which took a little effort to prove. So I'll just share it with you for now. It says the way to tell just by looking at a picture whether it will work. If you can find any sort of loops like this with it's called a cycle in graph theory, where we got 4 or maybe 5 vertices all in a loop with none of the extra edges in the middle drawn in. If you can find that sort of thing, then it's impossible, just like you showed. And if you can find something like this, and what's special about this graph is that there are these 3 kind of outliers. And the trick is you can get from any outlier to any other one without coming anywhere close to the third. See, we can get from this first one to the third one, and we always have a little buffer in between our path and that third outlier. If that happens, then it's impossible. Then it basically leads to this kind of problem. And if those are the only 2 obstacles, if those obstacles aren't present in your picture, then it works. All right, so Dalton, let's turn this thing back around. All right, so we've got 2 tasks. The first is to clean up this graph right there. So that's a mess. It would really be nice if someone could untangle it for us, like redraw it in a different way so that there's not all of these edges crossing over each other. So that's your first task. Draw a cleaner version of the graph so that we can really analyze it without a lot of difficulty. And then we'll start looking for those problem spots now that you know what to look for. That's a big improvement. Will you draw that for us? There's still a little crossover, but it's much better. Oh, that's right. So Hannah's got. She just came to her in the dream. There you go. So go ahead and draw it. She's put the points in a different order, and it helped to untangle the picture a lot. Except I want to make you draw it real big. So put B way over there. Let's see. Nice big picture. I'll help you draw in some connections. You're going there. I'll start at the bottom. So F connects to C. D connects to F also. Yeah, D connects to A. C connects to D and F. Let's get the C to D. And B, we got A, F, and A, B. Oh, we got A, B, and A connects to E. Okay. So you can see this is an improvement. Can you recommend maybe one more little? Oh, like if we just, in fact, if we just drew this edge kind of around like that, or maybe we could pull D all the way over to here.
Or E, you can pull E that way, or you can pull D that way.
Oh, I see, kind of bring E in towards the middle.
Yeah, if you just bring it all the way past all the others. So you say yeah, all the way up there. And that will do it.
Oh, that would do it. So A was connected to D still. Let's try that. Let's put E over there. And then it could connect up to everything without getting in the way. So E is going to connect to A, B, F, and C. Go ahead and draw that in. I'll try to do this. Oh. Well, that's a lot nicer. In fact, it even has a little bit of symmetry. Is that symmetrical? Now, look carefully at this. Is that an interval graph or a timeline graph? Is there a... are there any of those obstacles we just talked about that would... Where are the problems? Oh, there's a... Right? Here's a problem. A, B, F, D. There's one of those squares there, and we already know that that's impossible. I'm going to highlight it. This is bad. Is there any other trouble lurking in this picture? So right away we know someone was lying, right? There's no way this can be a timeline, have come from a real timeline. Are there any other obstacles here? Well, we only see triangles that are left. That's even a triangle there. It's a little hard to tell. Okay. Next question. That means, what are we going to do? Remember, there's one extra edge in here. One person made up a sighting. That means that somewhere there's an extra edge that shouldn't actually be there. And now the question is, which is the bad edge? Which represents the fictitious sighting?
If they lie about both, or just one?
Just one. There is only a single bit of misinformation here. So this is where, I think it was Valerie, this is where Valerie's idea comes in. Let's just try one. Pick an edge that could have been, that we might take out to get rid of this problem. What if we take out AB? So now, is there any problem with this graph? Where's the problem? Yeah, now there's this big loop here. And that's one of those, I was talking about, one of those big loops, one of those cycles that has nothing in the middle. And you get into trouble. So this is still impossible. In other words, that couldn't have been a single lie because we don't wind up with something that works. All right, so
take out B, it makes just B, or BF, makes a big number.
Yeah, what if you take out BF? Right, and so, what Andrew, I was like, no, Sam's over there. What Andrew's saying is, oh, look, now we just have a triangle. So are we okay now?
Except it still has points in it.
So you're saying that's actually not a triangle?
Because if you move it, then it's not a triangle. You move the points.
Oh, in other words, it's like if you just look at, you're saying that this and this don't somehow
It's not.
become a single edge. It really is 5 people in a little ring. And that and that becomes more clear if you move the B and yeah, it's still a problem. That's not the trouble spot.
You need to get rid of D.
So you want to get rid of DA. Does that get rid of the issue? Now, are there any of these loops? That cleans it up. There are, this one wouldn't have worked either, right? We would have gotten this big thing. There's the lie. Now it's time to find out who swiped the flash drive, because Emily wants it back. Is it, well, like how do you know it was D and not A?
Because I didn't say I saw it.
Oh, A never said they saw D. It was D that said they saw A. And so, D, where's D? Just kidding. Oh, look, you were volunteered, right? You did, Sailor. So there it is. We have, using what's a graph theory analysis, we have, hang on, let's see. We actually have identified the culprit. And it's a happy ending, you'll be glad to hear, because Eric, turns out, was only trying to do Emily a favor because he was going off the printer project and get it in on time because he realized she left it. And it was like, you know, it was all misunderstanding, so it's okay. But that is what I wanted to play with today. Thank you very much, and I hope you had fun playing.